I'm thinking of a problem. It's a geometry problem. Imagine a surface. I can measure its area, but it doesn't have any edges. You got that? It has a finite area, but no edges. What is it? It's not a square. It's not a circle. It's none of these. They all have edges. The one I'm thinking about doesn't have any. I'm thinking about a spherical surface. No edges. See? A sphere is a pretty interesting surface. Why? Because we live on one. Since our species first walked the planet, we've been exploring this surface. We invented mathematics to help us. In fact, geometry means measuring the earth. For thousands of years, we've used mathematics to measure and map the planet. In fact, we'd be lost without it.
I think most people take maps for granted. People who make maps don't at all.
Nigel Holmes is a map maker for Time magazine and newspapers like the New York Times. His maps link millions of readers to places and events across America and around the planet.
The kind of maps that I do, they're going to say, this is where the explosion happened. This is where the plane crashed. That's the kind of job that I do. Maps actually show relationships between things. That's what I like about them. And very concrete relationships. They show you the edges of things. They show you where you are. I'm a bit of a nervous traveler. So one way that I'm going to calm that down is, at the very least, is to know where I am. If we can see something in front of us, we do feel more relaxed about it. I'm going to show you the perfect map. Ta-da! It's a globe. It's not flat at all. It's perfect because everything is in the right proportion to each other and there's no distortion. But if you wanted to use this as a map to get you from New York to Washington, you can barely see that there's any detail in there at all. Actually, you'd have to go to something enormously bigger than that if you wanted to see the detail. Maybe to something like this, although even at the size that I've got this thing, there still isn't enough detail for you to see New York to Washington. What's more, I feel slightly stupid coming into the room here with this and saying, okay, love, we've got the map, now let's go off on our road trip. The perfect map would be exactly the same size as the thing that you're mapping. Obviously, you don't do that. You make a scale version in which one unit on the map represents many units on the ground. And it's this mathematical scale that gives a map its authority. It gives the reader of the map the belief that the map is really going to get them from point A to point B.
Mathematical scale solves the size problem, but getting rid of distortion is another mathematical challenge.
So here's the problem, what we professional cartographers refer to as the orange peel problem. You want to map what's on the outside of it onto a piece of flat paper. If you take the skin of the Earth off it and put it down on the ground, it's not flat. It isn't a flat thing. I mean, as much as you try to flatten it, it kind of sticks up. And this is the problem that all cartographers have to deal with, all people who make maps. It's a basic geometry problem.
Over thousands of years, cartographers have devised clever formulas that describe how points from one surface can be transferred to another. Some project these points onto a cylinder. Others project them on a cone. Still others project points directly to the plane. But there's no perfect way to flatten the Earth. Every projection has some distortion. A famous example is a map made by Gerardus Mercator in 1569. Any line drawn across it would show a constant compass direction, and for centuries sailors used it to chart courses around the world.
Mercator's become synonymous with map. Mercator equals map. Most schoolrooms had Mercator projections in them. People even knew the name Mercator. I mean, he was a famous person. And an example of the huge distortion on Mercator maps is shown here with Greenland. Greenland is actually the size of Mexico. And you can see how enormous it's got here because of the distortion of the particular projection that was never meant to show the relative sizes of the countries, was meant as a navigational tool. There are all sorts of maps, some good, some bad, some quirky. But all of these start from somebody measuring something. The way you represent that measurement, that mathematical measurement, can take so many different forms that the scope of the word map is enormous.
Here's the airfield at Sarajevo. Okay, last start there. Yeah. It's exactly 42.7 miles at 024 degrees.
Okay, short flight.
Roughly about 50-mile flight.
When you're racing around at 500 miles an hour at low altitudes, the more you know about where you're going, the less chance you'll make a mistake or miss the target. And especially at night in adverse weather, it's very, very critical to know where you are and where the terrain is.
Over centuries, the science of map-making has become very sophisticated. To help pilots rehearse their missions, the military uses mathematics to make what may be the most realistic maps ever made.
I do think of things mathematically in some cases because you've got to build, in essence, models. And as we all know, when you build a model, there are certain mathematical equations. You've got to build a model of the airplane, which simulates what the airplane actually does. But there's also a very complex mathematical model of the Earth, a three-dimensional model of what the terrain looks like made up with equations, figuring out how high and how fast your airplane can climb over the terrain.
Satellite images and intelligence data are layered like pages of a book to create a map that looks as real as the ground it represents.